podcast. Okay, and thanks Chairman kind of introduction. And hello everyone. My name is Ho Changchen. I'm from Taiwan, the graduate student of Department of Forestry, National Zhongxin University. Today, I would like to talk about application of spatial modeling approaches, sampling strategy, and the 3S technology within an ecological framework. And there are 6 parts in my presentation, which is from introduction to conclusion. And before we talk today's topic, I want to share everyone a short movie about the loss of the biodiversity in our world. Please enjoy it. The world species are dying out at a running rate up to 1,000 times faster than their natural rate of extinction. And so many species will face that problem and suffer the stress. And according to the survey, about 5,200 animal species and 34 plant species will face the problem and suffer the stress in the future. And that's the problem, cause the problem, partially due to the human change the species habit, polluting, hunting, global warming, introducing invasive species, and the deforestation. But why we need so care? Because our healthy economy and the society always depends on the variance of the ecosystem service. We need have designed a plan to tackle this problem. It's time you and me to make a change in our worlds. And I have to say, the best strategy is integrate advanced technology, sustainable target, and rule of knowledge to achieve it. So we think we have to, and we have time, and we have plan to do that. And this is our today's topic, and I want to share everyone. And in terms of forest, we use one workable framework, species distribution model. It becomes essential tool and how many dimensions. Like you could target the field words and the assist of conservation planning and explore the potential consequence of the climate change. In addition, we integrate the 3S technology and the statistical tool, gradually enhance the worker capacity to meet that challenge, giving the ability to describe a pattern in natural over broader spatial scale than ever before. So now we have a new plan for to organize the data resource. We record the data by the GPS and broadly use the remote sensing information and integrate all the attribute data input the GIS to analysis and interpretation. But even we have better than the traditional manner, it is still hard to describe the species pattern accurately, since we always suffer the problems below, like species trait have been proved will influence the success of the prediction. Such influence have ecological rule, some category better than the category. And the different methods, of course, have different modeling results. We need evaluation and comparison. And more importantly, environmental variables contribute a different importance for the species. And that study focuses on the latter two and to know the effect. And the target species, which is from the central Taiwan, is a widespread species. Its name is Chinese Goga tree, and that we call the CGT. CGT can grow in the wild geography and the geography and development range. And CGT also have excellent fire resistant traits and can grow in forests to form a fire land. And that's our go-to on-site to target and to data log the tree species sample. And the model, we choose the maximum entropy in that study because it's a promising new method for recently publication. And we also use the domain and generalized linear model and the artificial neural network as the basis for comparison. In brief talk, we use the full model to predict the potential habit of Chinese Goga trees. Then what kind of variable we should be select for model development? According to forest ecology, the plant habit is roughly composed of including soil, biotic, topography, and the climate factors. And at the primary stage, topographic variable is the first choice because it's easily to obtain and could generate from the DEN. So in our study, we first chose using the topographic variable. And the end of the study, we try to check the 3 points. That's including which models are used for plant species, how the ability of spatial extrapolation with models, and how they affect the topography to influence the model performance. And that's what we want to know. And the study area, let's show you, is a rectangle shape, which encompasses the Huishun forestation, and the total area is 17,136 hectares. And Huishun forestation is a representative forest in central Taiwan. It's a very high biodiversity and also have a complex microterrain. You can see the elevation range from 444 to 2480 meters in a small area. And so far, we collect the CGT sample. We'll collect from the 3 places. That's including Dongfeng, Yousheng, and the Guandao sites. And further, I want to that's the study, the flow chart in that study. First, concerning the database creation, we generate 5 predict variables. That's including elevation, slope, sap, terrain position, and the vegetation index. And the elevation, slope, and sap was generated from the DEN, and the terrain position we digitizing and also photo, and using the Euclidean relative distance to generate. And the vegetation index is from 2 SPAVA images to generate. And the second, the species sample were obtained by the GPS, and we're using the post-process differential collection. And so far, all the CGT sample and the total number we get 122 from the Dongfeng site, and the 8 sample from the Yousheng site, and the 64 from the Guandao site. And we further to combine this data point and further to make sampling design. And as I showed you before that study map, at the beginning, we spread the Dongfeng data. We randomly choose 2/3 Dongfeng data for the model development, and that we call the Dongfeng-based model. And the remaining Dongfeng sample were used for model validation. And the second design, we use the same Dongfeng sample used for model development, and the test data taken from the Yousheng site for model validation. And the third one, we keep the same Dongfeng-based model used for model development, while the test data far from the Guandao site for model validation. That's a series designed to detect the relationship between the different spatial scale and the model performance. And that process will repeat 3 times to get the mean value and make model robustness. And that slide show you, we overlay all the layers and to cut the CGT suitable and unsuitable environment attribute data. And we integrate those environment attribute data into the models to calculate model parameters. And I further to summarize that table to show you the different model classification methods and the features. Please first seeing the maxim models. That model core idea is using the entropy value and the Bayes probability. And it's a promising new method. It's trying to find the optimal species density under the constraint condition. And recently always using that model. And the second, domain use the point-to-point similarity metric. It can give all sites have similarity value and set the threshold to cut the confidence interval so we can realize the condition and to modeling the species distribution. And the third one, GLN is a nonlinear regression model. Of course, it's a regression model and it's a flexible generalization of ordinary linear regression. And they have the 3 components, that's including random, systematic, and the linking function. Especially the linking function, we use the logistic regression. You could switch to the binary to model a binary variable and to model yes suitable and non-suitable habit. And that's the one. And we use the back propagation algorithm. And let exhibit some brain-like behavior and auto-refracting and modeling any possible resource. And we set the 4 layers, that's including 1 input layer, 2 hidden layers, and the last one is output layers. Finally, the result need comparison and the validation. So we use the test data and take the kappa measure. And kappa measure could celebrate 5 labels, that's including from the lower to high and almost 5 labels. And we check the 3 points. That's including which models are used for plant species, how the ability of spatial extrapolation is modeled, and how the effect of topography are variable to the model performance. And next part, I want to talk our study result and the finding. And if we, as mentioned before, we talk the total number should be around 118 possible combination. That's a large amount of data calculation. So we try to reduce our data dimension and help improve the data efficiency. And we follow on this table the relatively important variable in this model, unfortunately except for the AN model, because we use the free software module and they don't offer that the contribution, that function. And overall, we could see the relative elevation, slope, and the terrain position have relative high importance for modeling the Chinese Boga tree. So if using the 3 predictor variable to build our models, and that graphic show you the relationship between the 3 sampling design and the 4 model performance. And the SD1, 2, and 3 is mean from the Dongfeng, Yousheng, and the Guangdong test the data sets. Generally, in 3 broken lines, we can find they have similar change by the mean kappa value, and we find the 2 effects in that graphic. First point, the model have different prediction ability. We rank model performance from high to low. We could find maxing and domain were much better than the GON, and last one was the ANN. And the second point, the model performance decrease with increase the spatial extent. So if we predict the small spatial scale, the model can good performance. But when we extend some spatial scale, and they will dramatic decrease and eventually near to 0, and finally lost the prediction powers. And the second, if we consider cost benefit, of course we should do that. And we find the maxN and the domain 2 model were much better because they have that's a good prediction ability, and their prediction map can offer the prediction map can set a level and a cost in the future investigation from the total area. So we think these 2 models were much better. And in addition, we try to visualize and to link our data resource. We make an example. The dark green is our non-suitable habit, and the orange color is our suitable habit. And the sky blue and the red color blue point is our CGT sample. And we add in including the pink and the black green triangle is our background non-suitable habit. And we launched the 3 specific areas to compare the model performance by the omission and the commission error. And let's go to see in the SD1 case. And we find in the small spatial scale, all the model can predict very well and could significantly decrease the omission and the commission error. You can see the domain, GON, and ANN have a similar chance with the maxN. And the second, we try to extend some spatial extent, and we find the model deeply increase the omission error in the upper right side. We find maxN and domain and GON and ANN. At the same time, the wrong prediction with the background increase the commission error with non-suitable habit. So when we try to over some spatial extent, and we find the model will both increase omission and commission error. And further, we try to use far from another place the Guangdong test data set, and we find total model cannot predict very well. You can see the CGT sample totally wrong predicts is that another place and non-suitable habit, no matter domain, maxN or GON, maybe ANN, they also cannot predict very well. That indicates no model can predict very well when we offer the model prediction spatial extent. So the model, if based on the topographic variable, they only apply it within the limit geographic extent, cannot predict, can predict very well. But when you try to over predict, they will lose their prediction powers. And finally, I drew some conclusion. And let's go to see the first point. we rank the model performance in a small spatial scale, and we find a maxN and a domain 2 model were much better for predicting a Chinese Goga tree. And in addition, if we consider cost and benefit, the maxN and domain 2 model were much better because they could set the cost and level in the future investigation might be used for conservation planning or the management tool. The second, we try to know the relationship, the different spatial scale and the model performance. Of course, we find that point, each model can predict very well in the modeling the small spatial scale. And when we try to extend some spatial scale like SD2 and SD3, the model accuracy declined sharply and eventually near to the zero. That means no model can predict very well when you over-predict their spatial extended range and they lose their prediction powers. And as we find, the model is based on the topographic variable that only applied it within the limit geographic extent and can predict very well. But when you try to over-predict the other and cross another place, they will lose their prediction ability and causing the missing linking. And that study, instead of primary stage, we still lose some key factor and not take consideration. And future will improve our data quality and try to add in the direct predictors and also attempt to use the high spatial resolution and hyperspec image data and try to improve our model performance and could apply it using a large spatial scale. And that's my today's topic. Thank you for your attention.
Yes, just what do you mean by terrain position? Maybe I didn't hear it. And what did you mean by terrain position?
Terrain position.
Terrain position.
Oh, terrain. Okay, thanks. Sorry, I have echo, so I cannot listen clearly. The terrain position we use that idea. Let's show the mountain size. We partition A section from valley to ridge, and we using the digitizing the method. We get to digitizing our study area and the valley and the ridge, then to transfer the raster layer. And we use the formula these days, the Euclidean relative distance to get that raster layer and to calculating our terrain position. Okay. That is our idea. Yes.
Did you just remind me? Did you sample the locations of the trees? You took obviously habitat information for every one of the trees that you measured in all three of those regions.
Yes.
Yeah. Okay. So I'm just wondering whether the trees might actually be doing something different in one part of the landscape than another. So they might be preferring a different habitat for a different reason in another part, in another region.
Yes, of course.
Yeah.
So we know that different the species in the different landscape have the micro terrain, we said adaptations. Yeah, we know. But we try to find the species, the range, the preference, and to modeling according to a small spatial sample size and try to know that place, that preferring the environment. That's our to want to know. Yes. Thank you. Comment.
There's time for another question.